ahead and record this. The focus of chapter 4 is triangles. And so I want to go through... Okay, I want to go through first in section 4:1. Jesse. I want to go through and look at some vocabulary terms. There are a few theorems and postulates. And on that sheet that I gave you, if you just keep on going down the sheet into chapter 4, this stuff is all on there. Okay. But I want to make you aware of a few relationships, some vocabulary, sort of an introductory section at first here. And then we'll start to get into, in 4.2 and 4.3 and beyond, we'll get into some more specific areas. Okay. So triangles and angles. All right, we want to be able to classify triangles in two ways. We want to be able to classify triangles by their sides and by their angles. And most of this stuff you probably already know. And we want to be able to find some angle measures in triangles. Definition, a triangle is a figure formed by three segments joining three non-collinear points. Okay, so the vertices of the triangle, or obviously if it's a triangle, they can't all line up on a single line. They can't be collinear. They have to be, any two of those could be on a line, but the third one, if it's going to make a triangle, has to be off of the line. For example, if these are two of the vertices of a triangle, well, the third one can't be on that line, or it's not a triangle. It's got to be up there somewhere, right? So those three vertices that are joined by the sides of the triangle must be, of course, non-collinear. Okay. All right. So some names. We're just going to classify these things a little bit. If we look at the sides of a triangle, there's some different ways we can classify them. Equilateral means that a triangle has three congruent sides. Okay, there are three sides that are the same length. And that's exactly what that says, by the way. Equa means equal, and lateral means side. So it means equal sides. An isosceles triangle, and you're probably familiar with this also, an isosceles triangle is one where we have two congruent sides. And if we wanted to mark this up, we could do something like that, right? All three of those sides are congruent, but only two of those sides are congruent. A scalene triangle is one where there are no congruent sides. They're all different. So those are the three ways we can classify triangles by their sides. Probably review. Okay, what about by angles? An acute triangle is one that has, an acute triangle is one that has all three angles are acute. So in this case, notice that measure of angle ABC, we could just call that angle B, I guess, couldn't we? Measure of angle B is 70.26 degrees, less than 90. Measure of angle CAB, which we could just call angle A if we wanted in this case, 41.76, less than 90. And then measure the last angle, angle C, or BCA if you want to, is also less than 90. So all three of the angles are less than 90 if it's acute. What if it's equiangular? What's that? If we just look at that means equal, angular, angles, right? All three of the angles have equal measures, and so they're all congruent. So we could do this. If that's true, if all three angles are congruent, then it's equiangular. Okay. Now, that has to be acute also, doesn't it? Just going, we haven't talked about this yet in this class, but I'm sure you've talked about this before. What's the sum of the interior angles in a triangle? 180, sure. So then if it's equiangular, if all three angles are congruent, what must they all be? 60. Yeah, they'd have to be, wouldn't it? Because they all have to add up to 180. And so 60 is less than 90, so of course this is going to be acute. Notice that these classifications overlap a lot. In a triangle, we could classify this as being equilateral, sure. Equiangular, that works also. And acute, they all work. A right triangle is one that has exactly one right angle. What about the other two angles then? What could you say for sure about them? They have to be acute, don't they? Because if this one is right, so it's 90 degrees, the other two have to add up to 90. Yeah, exactly. And so if they have to add up to 90, neither one of them could be 90 or bigger. They both have to be less than 90. Okay, an obtuse triangle is one that's going to have one big obtuse angle, right? And then, of course, the other two would be what? Acute. Yeah, if this angle is bigger than 90 and there's only 180 degrees to go around, the other two have got to be smaller, right? All right, so is that, you've talked about this stuff before, I'm assuming, right? This is going to be reviewed a little bit. Good. Okay, the parts of a triangle. What's the anatomy of a triangle here? If we're going to refer to, let's sort of focus on angle A here. Each of the 3 points joining the sides of a triangle is a vertex. So we have 3 vertices. That's plural for that, vertices. But that's a vertex A, that's vertex B, that's vertex C. Plural vertices. We know, of course, that the segments joining the vertices are called what? What are the segments that join the vertices? For example, the segment that joins vertex B and vertex C, what do we call that segment? Of what of the triangle? Side, sure. So the sides of the triangle are just the segments that are joined together at the vertices. Two sides sharing a common vertex are what we call adjacent sides. Okay? So for example, if we're talking about vertex A here, we would say that both of the blue sides are sides that are adjacent to angle A. Okay, because they're next to it. Angle A is a part of both of those sides. But the red side over here is what we call the opposite side. That's the side that's looking at angle A and vice versa. Okay, it really makes sense when we call that opposite. Okay, for a right triangle, we've got to get a little more specific. For a right triangle, and we've already sort of talked about this. If this is the right angle, here, then the side opposite the right angle is always the hypotenuse, right? And then the other sides of a right triangle we call the legs. What about an isosceles triangle? For an isosceles triangle, the two sides that are congruent, I need to put those congruences in there. So if these are the two sides that are congruent, we call those the legs of the isosceles triangle. And the third side, the one that's not congruent to the other two, we call the base. So you always want to think about it in your mind. You always want to think about taking an isosceles triangle and setting it on a table on the base so that the two congruent sides, the legs, are up in the air off the table. That's a convenient way to think about it. Okay? And then let's go ahead and now that we've sort of talked about the vocabulary a little bit, let's do some stuff with this. So here we have a picture. I don't know what this is supposed to be, but it's some kind of a structure of some kind here. So first of all, if this is vertex A, that's B, and that's C, why is triangle ABC an isosceles right triangle? Okay, we know that it's isosceles because I've got what now? Two sides that are congruent. They have the same length, right? So that makes it isosceles, and then what makes it a right triangle, of course? Yeah, that I've got a 90-degree angle. Okay, good. In the diagram, you're given that angle C is a right angle. By definition, then we know triangle ABC is a right triangle. Yeah, I mean, we got that one covered. No big deal. Okay. How about this? Identify the legs and the hypotenuse of triangle ABC. We've already determined it's a right triangle. And so, of course, we know then that the hypotenuse has to be the side opposite the right angle. Turns out it's also the base in this case, isn't it? Because it's an isosceles triangle, and so it's the base of the isosceles triangle. It's the oddball side, the one that's 7 while the other two are 5, right? But then it turns out it's also the hypotenuse. The legs of the isosceles triangle in this case are also the legs of the right triangle. Okay. All right. Okay, what about these other angles? I didn't make this, I promise. If we've got a triangle here, now look what we've done with this. We've got a triangle, and then we've extended each of the sides of the triangle so that they're not segments, but they're rays, right? So if we labeled this thing, this is a B. You can't really see it back there, but let me draw that in. So for example, vertex B, instead of drawing segment BC, we're going to draw ray BC. Instead of drawing segment CA, we're going to draw ray CA. And instead of segment AB, it's ray AB. If we continue those out there, then not only do we have the 3 angles that are trapped inside the triangle, which we're going to know from here on as interior angles because they're inside the triangle, we also create these angles outside the triangle. Okay, and so in this case, the smiley faces are the interior angles, and the hearts are the exterior angles. Notice that these are the angles that are obtuse. They're less than, they're greater than 90, but they're less than 180. We're not talking about these straight angles over here. They're always the ones that are less than 180. Okay. Now, how do you know? You might be thinking, okay, well, how do I know that I'm going to start at A and make my ray through B and not vice versa? I could have also done this, couldn't I? I could have also taken this ray and gone that way with it. And I could have gone this way with that one, or that way with that one. Well, it doesn't matter. It doesn't matter, does it? Because this exterior angle here is the same as that exterior angle there. They're vertical angles, aren't they? Right? So it doesn't really matter. It doesn't matter. You can do this anyway, as long as you just take one side of the triangle and extend it out as a ray. Whatever angle you make there that's less than 180 is going to be the exterior angle that goes with that vertex. Okay? So what do we do with these exterior angles? Okay, we have an exterior angle theorem that comes in handy. Now, in this case, if we've got this triangle, and we've got this exterior angle 1, the angle that we make when we extend the base of this triangle beyond the triangle, right? The angle that we make that's less than 180 with the triangle, there it is, angle 1. It's an exterior angle. One thing we know about exterior angle 1 is that the measure of this exterior angle is equal to the sums of the measures of what we call the remote interior angles. In other words, the ones that are not next to it. The 2 angles that are not adjacent to that exterior angle add up to the same measure as the exterior angle. Okay, so in this case, measure of angle 1 must equal the measure of angle 2 plus the measure of angle 3. Now we can use that to do some algebra type problems. Like, for example, if we want to solve for x in this situation. And if we're able to solve for x, we're able to solve for the triangle. We're able to determine what are the measures of these angles exactly. That one's 65, but what's that one going to be? And even what's that one going to be, if we want to? By solving for x, we can plug that value back in and get the measures of all these things. Well, does it make sense now we could use the exterior angle theorem we just talked about? We know that this exterior angle, which has a measure of 2x plus 10, has to equal measure of angle, this angle here, this bottom left angle, and the measure of this top angle. So x plus 65. Right? We get an algebra equation out of this that comes from the geometry relationship, real similar to what we did last chapter. So x plus 65 equals 2x plus 10. We can do a little algebra. Right? I could subtract x from both sides and get 65 equals x plus 10, subtract 10 from both sides, and get x equals 55. right? So now I know, once I know that x is 55, I can figure out what this is, right? 2 times 55 is what, 110? Plus 10 is 120. So this exterior angle has a measure of 120. Yes?
I don't know if this is right. Can you just do like 180, like do like plus 10?
Say it again. You're on to something there.
Supplementary.
Yeah, you can. You mean for this one right here now?
Yeah.
Yeah, you can, sure. Now we see that these form a linear pair, don't we? Right? And so if this one's 120, what must this angle be? Has to be 60, doesn't it? Because they have to add up to 180. They're supplementary, so we could fill that in. What's another way we could have gotten that angle without even using the exterior angle? The interior angles, their measures has to be 180 also. Sure, so we could have gotten it either way. Okay, good. How could we do this then? We know, let's say we know that this is a right triangle. So let me indicate that. Okay, there's a corollary to the triangle sum theorem that we've already used actually. You already know this. You know that the sum of the interior angles of a triangle is 180, right? If it's a right triangle, then that means that one angle comprises 90 degrees. What do the other two have to add up to? 90, right? So then couldn't we say something like this? The measure of angle A plus the measure of angle B has to equal 90, right? Well, that's just x plus 2x, right? So then if I solve for x, how am I going to do that? Add the x's. So 3x equals 90. Therefore, x is 30 if I divide both sides by 3. And so I could fill in the blanks. This angle down here is 30 degrees, and this one must be 60. So we can solve for the triangle there pretty easily. Okay. All right. So that's just a little introduction there to some terminology. Let's take a quick look at some other stuff we can do with that. Okay, take a closer look at congruence within triangles and congruence between triangles. So our goal here is we want to be able to identify congruent figures, not just something simple like lines, but now figures like triangles, or even something bigger than that, some figures that might be quadrilaterals. And we want to be able to prove that two triangles are congruent. Okay, so first of all, what does it mean to be congruent? It's a simple but important definition. Two geometric things, we call them figures, two geometric things that we could draw or point to, are congruent if they have exactly the same shape and size. It needs both parts of that, same shape and size. Now, later on in the class, we'll look at some cases where two geometric figures might have the same shape but not the same size, and we'll call those similar figures, but not congruent. If they have the same size but not the same shape, well then, they're nothing important really. They're certainly not congruent. So here's an example of three congruent shapes. And the simple sort of visual test you can always do to see if they're congruent is imagine this. Imagine if I pick this piece up and I twist it around, I could even flip it backwards if I want to. Could I take this cardboard cutout and set it on top of this one or this one so that they overlap perfectly? If you can, then they're congruent, right? So these are all congruent. These obviously aren't. Those are, not only are they, they're not even the same shapes. They have to be the same shape and the same size to be congruent. Okay, when two figures are congruent, then there's a lot of stuff we know about them. It means that every little part of each figure correlates to a part on the other figure. So, for example, all of the sides that correspond are congruent, and so are all of the angles. Okay, and we just call those corresponding angles and corresponding sides. For example, if we know that triangle ABC is congruent to triangle PQR, then we know a lot of stuff. We know that because angle A corresponds to angle P, when I overlap the two, that angle A and angle P must be congruent. Same thing for C and R. Angle C must be congruent to angle R, and angle B must be congruent to angle Q. So the angles are all congruent, so are the sides. When I pick up the first one and set it down, because side AB overlaps with side PQ, well, those must be congruent. Side AB is congruent to side PQ. And we can say the same thing about the other two sides also. So we get all 6 of these pieces of information come with the congruence of those two triangles. Okay, there's more than one way to write a congruent statement, but what's important about it is that you have to line up the corresponding parts. So for example, in that last situation we looked at, we have to say, if I'm going to write the first triangle as triangle A, B, C, and I want to write a congruence relationship, if I've picked the vertices in that particular order, first A, then B, then C, that dictates the order for the second triangle also, because I have to use the corresponding order. I've got to use triangle, well, A goes with P, right? So I've got to put the P first. B goes with Q, so I got to put the Q second. And C goes with R, so I got to put the R third. Now, I could have done it differently, and that's fine. It would have been okay to say this also. I could have said triangle BAC is congruent to what? Okay, Q. B goes with Q. P. And then C goes with R. And that would have been fine also. Okay, but you have to have the same order. Does that make sense? Now, the other thing that comes with that, when you line up the vertices, it tells you a lot of stuff. Without even drawing the triangles then, I know that angle A must be congruent to angle P, right? Angle B must be congruent to Q, and angle C must be congruent to angle R, without even drawing them. I just know that has to be true. I know that side AB would be congruent to side PQ also, for example. Okay? Okay, how do we write a congruent statement? Well, we just looked at that. So, real quick, just try that. Don't say it out loud, but I want you to come up with a congruent statement. Triangle what is congruent to triangle what? What do you think? What's one way to say that those triangles are congruent? What do you think, Dylan?
Angle DEF is congruent to RST.
Good. Okay. It's a little tricky, but notice here that D, because D has double congruence arcs on it, and so does R. We can see that D and R go together, E and S go together, and F and T have triple congruence arcs, so they go together. So we could say triangle, how'd you say that again? DEF. Is congruent to triangle RST. Good. Okay, good. Now, either by looking at the triangles or just by looking at the congruent statement, what are the corresponding parts, the congruent corresponding parts? I mean, we already said the angles pretty much. Angle D is congruent to angle R, etc. Okay, and we did the angles. What about segment or side EF? What's EF congruent to? ST. We can see it right there because that's the second and the third vertices. So it would be the same over here. What about side FD? TR. Either by looking at the picture or just by looking up here. Okay? Okay, so there's all the congruent stuff that we can come up with. And I'll have this PowerPoint's already on the website if you want to look back at it. Okay, now let's use the properties of congruent figures to do some stuff. First of all, if we're told, this is something we're given here, we're given that figure NPLM is congruent to figure EFGH. Okay, so that tells us a lot of stuff. We want to use that information to find the value of x. Okay, now don't look over here for a second. See if you can get that to work. See if you can think of a way you could do that. I want to find the value of x. Well, notice that the x is showing up. There's the x. Okay? X is in that. I don't know why that m is there. We don't really need that. Oh, it's in meters. So length in meters. Okay. Okay. So how are we gonna do this? If I want to solve for x, what can I do? If I know that these two figures are congruent, then I know all the corresponding parts are also congruent. Right? So what's the specific relationship we're looking at here? Looks like x is included. 2x minus 3 is the length of side GH, right? So GH goes with what two vertices? LM, okay. So LM has a length of 8 meters. GH has a length of 2x minus 3 meters, so I can just set those equal to them. They're congruent. 8 equals 2x minus 3, add 3 to both sides, divide by 2, and I got it. X is 11 halves, 5.5. Okay. How could I, same deal, how could I find the value of y? Here's the y down there. It's part of an angle, looks like. Right, there's my y. 7y plus 9 is the measure of angle E. Angle E goes with which angle? So we can see here that n has a measure of 72. So 72 must equal 7y plus 9, and then the algebra is pretty simple. Subtract 9, divide by 7, and y equals 9. Okay. Okay, what about this now? Third angles theorem. This is really pretty intuitive, obvious stuff here. If any two angles of one triangle are congruent to the two angles of another triangle, then doesn't it just make sense that the third angles also have to be congruent? Yeah. Right? Because we know that the angles add up to 180, right? And so if I know, for example, that angles A is congruent to D and B is congruent to E, well, if the sum of those two has got to leave the same amount over as the sum of those two, because both triangles add up to 180, right? So it just makes sense. Okay, using the third angles theorem, find the value of x. This got moved around. I don't know how it got moved around, but it did. How could we do that? What do we know? Could I transfer some information from one triangle to the other if we're told here that these two triangles, well, we don't even have to be told for that matter. It doesn't even matter if we're told that they're congruent or not. We know that if two angles are congruent, so are the third, right? Okay, so then what this is supposed to be, this really got messed up. This one is supposed to be right there. So couldn't I say then that this one is just 65 and that one's 55? And now what could I do to solve this thing? If I want to solve for x, what do I know about the relationship of all three of these? Yeah, there's some of the measures is 180. So then 55 plus 65 plus 2x plus 30 has to equal 180, right? This is a little goofy the way this is written over here, but we could do that algebra really simply. Right, we could just say, let's do it right here. Or over here. If I know that 2x plus 30 plus 55 plus 65 equals 180, well, I could just, excuse me, subtract all that stuff away to the other side, couldn't I? 55 plus 65 is 110. No, 120. Plus 30 is 150. So if I subtract 150 from both sides, I'm just left with 2x over here and 30 over here. So what's x? 15, sure. No big deal. Okay. Okay. So last two are a little, now we're getting something just a tad bit more advanced here. Last two examples, you have to scratch your head about just a little bit. Proving triangles are congruent. So decide whether the triangles are congruent and justify your reasoning. Okay, so let's think about this first. This is what I'm given. I'm given that this angle's 92, that angle's 92, and I'm given some congruences among the sides. Okay, so I can see here, look what I can see. There's some hidden information that allows me to fill in all the stuff that I need. At this point, if I want to prove that these two triangles are congruent, the only way I can do it right now, and we're about to have some really good shortcuts in not today, but in a few days. Right now, the only way I can show that they're congruent is if I can demonstrate that all of the corresponding parts are congruent. Then, by the definition of congruence, if each corresponding part of this triangle and this triangle is congruent, then the two triangles must be congruent. Well, I got a lot of it. Look, I've got this side is congruent to this side, right? That guy and that guy. I've got this side is congruent to that side. Got that side is congruent to that side. So all three sides I've got. I've got one angle here, 92 and 92, but is there a way for me to get the other two angles? Right-hand idea. Do I see any angles that are also congruent, that I can prove are congruent? What do you think? Okay, yeah, right here. These are vertical angles, aren't they? Right, so these two angles right here are congruent because they're vertical angles. And so I know that if two angles of a triangle are congruent, then by the third angle theorem, the third angles must also be congruent. And so I got the whole thing. Now that I can see that I've got all three sides and all three angles can be shown to be congruent to corresponding sides and angles in the other triangle, I know those two triangles are congruent. Now what might that look like in a proof? Well, if I wanted to, I guess we don't do a proof of that one. That's okay. Let's do this one in a two-column proof format. Okay, what about this one? And the diagram represents triangular stamps. Prove that triangle AEB is congruent to triangle DEC. Here's what we're given. Here's the given information right here. This is important. So we're given that side AB is parallel to side DC. Okay, we know that side, I shouldn't have this up here, should I? Side AB is congruent to side DC, and we're told that E is the midpoint of segment BD, that should be, this is really messed up, BD and AC. Okay? So if we know that stuff, can we prove this thing? Well, let's see if we can talk through it first. Is there a way I could do that? If I know these two sides are congruent, does the midpoint stuff help me at all? It does. If E is the midpoint of AC, then what does that mean? Okay, it means that it's in the exact middle of that segment, and so it tells me that AE and CE are congruent, right? E is also the midpoint of BD, right? So it tells me that that segment and that segment must be congruent by just the definition of midpoint, right? Okay, so we got all three sides. That's good. What about the angles? Well, we know, what do we know? How could we do the angles? This is a little trickier. We got to go back to chapter 3 with this stuff. What do you think, Veronica?
Because it makes it perpendicular in the middle.
Oh, okay, in the middle. Because I've got these two lines that are crossing through point E, I can say that this angle and that angle are, is that what you're saying, vertical angles? Okay, so they're congruent. That's good. Now I need to just find, if there's a way I can show that angle A and angle C are congruent, and angle, I can't just say A really, can I? I got to say something like EAB and angle ECD. For example, how can I show those are congruent? What might be helpful here, this always helps for me, if we extend these sides out and make them look like lines, then look, I've got two parallel lines cut by a transversal. There's my transversal, right? So going back to chapter 3, what do we know? If two parallel lines are cut by a transversal, what's the relationship between angle EAB up here and angle ECD down here? What are those? What do we call those? No, not corresponding. Okay, I need everybody with me here, please. We got to reel you in here. This is this last big concept here. How can we connect chapter 3 to chapter 4? I've got two parallel lines cut by a transversal, and it looks like I'm looking at this angle up here, call it angle A, and this angle down here, angle B. Alternate interiors. Sure, there it is. Good. Okay, now let's remind ourselves why. Oh, they're alternate because they're on opposite sides of the transversal, right? And they're interior because they're inside the two parallel lines. Good. So we know that angle EAB is congruent to angle ECD by the alternate interior angle theorem, right? I don't care if it's a theorem or a postulate, they're alternate interior angles. Isn't the same thing true for this angle down here and that angle up there? Doesn't that make sense? Because now I've got this other transversal. Think of that as being the transversal, right? And I got it. I got all three angles are congruent to the other three corresponding angles. All three sides of this triangle are congruent to corresponding parts of this triangle, so we got it, right? So it should look like this then. If we wanted to look at that as a two-column proof, all this stuff is given to us. Segment AB and segment DC are parallel. Segment AB and segment DC are congruent. Okay, we said that we can show these other angles to be congruent by alternate interior angles theorem. We showed these angles on the inside here, these guys, to be congruent by vertical angles theorem. We're given the midpoint information. Well, if we know that E is the midpoint, you guys told me that means those are congruent and those are congruent, right? And then and this was given to us as being congruent. So we got it. Then we got all the sides and all the angles congruent. So by the definition of congruence. All right, I'm losing you. That's been a lot of stuff. A lot of stuff. That's where we can end it. That's good. Okay. The assignments are up.